and kind of see it. You'd see it twice, basically. You'd see it before you come in, you see it here, right? So that's out there. Yeah, no.
Thinking in terms of like the quizzes that you like to give. So usually, like you would watch the course video.
Mm-hmm.
You know what I mean? So does that mean that any quiz that we give is just kind of based on homework?
Quizzes will be off of homework or off of lecture.
Okay.
And that you've already done. Yeah, no, it won't be like, hey, we're going to talk about this today, but let's start with a quiz. No, I won't do that to you. I won't do that to you. But good question. I do expect, though, that after I've covered something and I assign the homework for it, by the next time we meet, that you're ready for a quiz on that. And if you're not ready, you can come to my office for office hours, which are on the syllabus, but I'll just tell you, today it's before our class for an hour, so from like 2 to 3. I'm also in my office from 11 till noon today, and then tomorrow I'm in there also, and you can make appointments. But look through the syllabus, and I encourage you to come and get help, all right? I'm here to help. I've tried to provide as many resources for you, but sometimes you just have to sit down and be there with a person, and why not have your instructor help you instead of a tutor, right? Yes.
Will the homework be on like my math lab?
Nope.
Out of the book?
Out of the book. I don't collect it. I don't grade it. I've already provided all the answers, right? They're all there. So yeah, it's really, this is grown-up math, right? So if you don't do the homework, that will be reflected on your exam grade for sure. It's not. I have historical data that shows that that's the truth. In fact, a couple of semesters ago, I had this habit at the end of Cal 2 to have my students write a letter to the next Cal 2 class coming in. And I would say, and I'm not exaggerating, almost 100% of those letters, the advice to the incoming Cal 2 students was, do your homework. If you've never had to do homework in the past, it doesn't matter. You will have to do your homework in this class to succeed. So, it's on you to do it. And, if you ever want, like if we are ever going to talk about bonus points or something like that, at the end of the semester you need like 2 points. One thing you could have is like your entire semester's worth of homework, like in a folder or something that you could prove to me that you were doing your homework. Things like that show me that you've been working would be good for you. All right. Anything else? Y'all feeling okay? All right. So I am going to start here with 3.5, which is inverse trigonometric functions, which was actually covered in pre-calculus. You should have been introduced to the idea of these inverse trig functions. Now, in pre-cal, I put over here on the side, there are 6 trig functions: sine, cosine, tangent, cotangent, cosecant, tangent, whatever, 6 of them. There they are. And then each of those functions has an inverse. So we're going to start talking about the inverses, and so we can remember some of the properties that we have to be careful with. And then really, because this is calculus and not pre-cal, we're more interested in the derivatives of the inverse trig functions. Because we already know the derivatives of all these, don't we? Right? From Cal 1, derivative of sine is cosine, derivative of cosine negative sine, derivative of tangent, secant squared, right? Those 3 you should know. Like, that should just come right out. The next 3, maybe you're not quite there, but you should at least know on your formula sheets where they are. All right? So those 6 we already know coming in here, but because there's 6 more trig functions, the arc sine, arc cosine, 6 more, we should know the derivatives of those. And those are going to come into play when we're trying to do antiderivatives. They're actually going to be very useful, these functions. So we will begin by just reminding ourselves of what a one-to-one function is. Basically, a one-to-one function is a function that passes both the vertical and horizontal line test at the same time. So if I have a function like a parabola, this function is not one-to-one because although it passes the vertical line test, what does the vertical line test say?
For a function to be a function, it must have one and only one point.
Yeah, if I draw any vertical line, I can only intersect it one time. And if it passes that, then it's a function of x. if I draw horizontal lines and hit more than one time, like here I would hit more than one time, then this is still a function, but the function has no inverse, and therefore it is not one-to-one. So one-to-one functions have to pass both of them. How about a circle? Is a circle a function? No, it's not even a function, right? And no inverse, it's not one-to-one. How about a sideways parabola? It's not a function. So what about inverse? Well, it passes the horizontal line test, but in order for a function to have an inverse, it must be a function to start. And this is not a function to start, is it? So this would not have an inverse because it's not a function. So something that would, so all of these are not one-to-one. Something that would, something like that. It would pass both the vertical line test and the horizontal line test at the same time. And if that happens, then we say it's one-to-one. And if it's one-to-one, we say it has an inverse. And if it has an inverse, that means that there is some function that undoes this function. It basically takes everything back to where it came from. I like to think about functions like car washes. You know, you take your dirty car into a car wash, goes through the function, the car wash, comes out the other side clean, right? The inverse function would be another car wash that you go through right after you get clean, and then you come back out and it's dirty. They put all the little dirt particles exactly back on your car where they were, right? That would be the inverse function. It undoes what the other one did. So in order to have an inverse, you must have this one-to-oneness. But in pre-cal, we defined, for all 6 trig functions, we defined inverses, didn't we? But to do it, we had to pay attention to the domain. So let's just talk about the sine function. I'm going to show you the picture of it here, and we can discuss it. So there's your sine function. It is a function because it passes the vertical line test. However, fails the horizontal line test, so it does not have an inverse. Not if we just look at it like that, right? Same with cosine. Cosine in here. Passes vertical, fails horizontal. Tangent. Passes vertical, right? But fails horizontal. And we could do that for all 6. So we had to do some sort of domain restrictions. Let me just show you a secant. You remember how those looked? The secant and the cosecant? All right, so in order to get around this, we had to restrict the domains. And I'm going to show you just how we restricted it for sine, and then remind you of what the restrictions were for the other ones. But sine will take a little bit of time on. So when we were looking at the sine curve, here it is, we can try and cut it off so that we can force it to be one-to-one. So I could just look at maybe this region. I don't know if you can tell it. It came in right here. See that? It's black instead of red. Can you all tell? I'll take the other one out. I'll take the red one out. Okay, if we look at the sine curve just there, then it's one-to-one, isn't it? And it also achieves every value in its range. It goes all the way from -1 all the way up to +1, right? So every value in its range is accounted for there. And that looks like we're between, what, like -pi/2 and, or I should start here, -3pi/2 and -pi/2. So if I just look at the sine function in here, I should be able to find an inverse function for that piece, right? All right, but why not pick another piece? How about we pick this one over here? That one would have worked just as well, wouldn't it? Right? And in fact, there's an infinite number of pieces I could have picked, right? So which one do we do? Just any one, arbitrary? We actually had to agree, okay? We all had to sit down at a table. It was, I don't know, Thursday night, I think, way back when somewhere. I'm just kidding. And all these guys sat down, and girls, of course, all sat down at this table and said, you know what? This is the one we're going to all agree upon. All right? Now, I don't know how it happened, but really, we all had to agree. All right? And this is what we agreed upon. This is the standard domain restriction for sine in order to define its inverse. If we didn't do it this way, then everyone would be getting different answers. All right? Because we'd have different domain restrictions. So we all said, look, if you just look between -pi/2 and pi/2, you will have a piece of the sine curve that achieves its entire range from -1 to +1. It's a one-to-one function in that little piece, just on that piece, we will define its inverse function. And we define it, and we have a special notation for it. We use either arc sine or sine with a little -1. I find myself using this one more, okay, but these are equivalent. And once we define it, then we have this relationship that the inverse sine of x equals y. This means if and only if sine of y equals x, and as long as the y is between -pi/2 and pi/2. So that's the key right there, is our restriction on the domain. Does that sound familiar? You remember that from pre-cal? All right, the graphs of these together. Does anyone remember if you graph a function and its inverse on the same axes, what they look like? There's some relationship. Yes, exactly. If we look at the very important function y equals x, which is called the identity function, y equals x is a diagonal, the perfect diagonal line. Okay, 1, 1, 2, 2, 3, 3. If we graph that, and then we graph both the sine function and its inverse, then they should be perfect reflections of each other over that identity function. So like mirror image of itself over that diagonal. All inverse functions graphed together with the original function have that property. All right, let's do these. So usually in my notes, I talk, and then I get to some examples, and I do those right here on the board. All right, so what's arc sine of 1? So what is this asking us? It's saying find the angle that you plug into the sine curve, or to the sine function, that would spit out a value of 1. So it's saying sine of what angle? I'm going to put a question mark. I could use a letter, but I'm just going to put a question mark. Sine of what is 1? Now there's two ways you can look at this. You can look at it from the graph of sine, or you can look at it from the unit circle. So let's take a vote. How many of you would prefer to try and figure this out using the graph of sine? That means like the wave curve. No? Okay, how many of you like the unit circle? Okay, I'm a fan of the unit circle. Big fan of the unit circle. But I'll show you both ways. Let me do the sine curve first. If I do the sine curve, here's our standard sine curve, right? And we're trying to figure out where it's 1, right? Where is it 1? Well, that happens here, and another one down here, another one over here. There's an infinite number of them, right? Places that it's 1. However, we have restricted the domain, haven't we? We've restricted it between pi/2 and -pi/2. That means we're just looking between here and here. And I think it's obvious from that it's happening at pi/2 then, right? So our answer should be pi/2. Great, fine, whatever, it's done. I don't like that way though. I like the unit circle, because the unit circle gives us some information. It gives us a relationship between angles, and it gives us both sine and cosine at the same time. And so does anyone remember if this is an angle, let's say theta, then the point here, the x-coordinate is what? Cosine of the angle. It's √2/2 if that's 45 degrees.
Yeah.
But in general, if you give me any angle, then the x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the angle. So what this is really asking me is what angle on the unit circle will give me a y value of 1. It's y value because it's sine. If this had been cosine, then we would be looking at the x value. So where on here is my y-coordinate 1, and that would be up here, wouldn't it? Because that's the point 0, 1. Obviously the y-coordinate's 1. And what is that angle? pi/2, 90 degrees, right? So we get the same answer that we got up here. All right, so that was kind of a trivial one, pi/2. How about the next one? Inverse sine or arc sine of √3/2. So this is asking the same question. It's saying, hey, sine of what angle is √3/2? So I come to my unit circle again. See, I'm not going to go to the graph. If you like the graph, go for it. I'm going to stick to this. So where on my unit circle is the x-coordinate? Y-coordinate? What is it? Y-coordinate. Where's the y-coordinate root 3 over 2? So you have to know where it is. That's going to be at pi over 3, 60 degrees. Right up here. That has an ordered pair of 1/2 root 3 over 2, right? That's not the only place, though, that your y-coordinate is root 3 over 2. It's root 3 over 2 over here, too. Because this is negative 1/2 root 3 over 2. So, you know, I have two possible candidates, but, what? Yeah, but there's a restriction, right? What we said is that in order for this to be defined, in order to be able to talk about an inverse, we have to restrict the domain on the sine curve, which means we are not allowed to look past pi over 2. So here's pi over 2, right? I cannot look past it. I must stay between negative pi over 2, which would be an angle turned clockwise, so down pi over 2, all the way up, or sorry, to negative pi over 2, and then all the way up to pi over 2. So basically, nothing in the second or third quadrants is allowed. And that forces you to have this answer. This angle is pi over 3. All right, so this would be, the answer here would be pi over 3. Got it? I would prefer the answer in radians.
Why did they do like the -1? Like, it seems kind of weird because I feel like that would be just 1 over sine.
Yes, okay. The question is why do we use that? Well, it actually goes back to when in college algebra, when we were talking about inverse functions, we actually used that notation when we were doing inverse functions. We used the -1 up there. But I agree with you, it's bad notation. It's bad notation because you can confuse that with something like x to the -1, which really means 1 over x. So when we've seen a -1 in this context, it means drop it down, right? But when we see a -1 in this context, it means the inverse function. So you have to kind of know what context that -1 is being used in, but I agree with you, it's bad notation. But you could argue there's a lot of other things that are bad notation. For example, if I write 2, 5, what am I talking about? Well, I could be talking about the point 2, 5, or I could be talking about an interval on the number line, everything between 2 and 5 without including the endpoints, because we use parentheses instead of brackets, remember that thing? So this is bad notation too, because it's not easy to just look at that and know what you're talking about. You would have to put something out here like x is an element of this interval. Then everyone knows it's an interval, but there's bad notation in math everywhere, all right? All right, so I want to do one more of these. I want to just change the problem up just slightly. I would like to do, instead of root 3 over 2, let's do negative root 3 over 2. So I didn't put a part C there, but that's your new part C. So this is asking, when is sine, right? Sine of what is negative root 3 over 2? So we're going to go and look at the unit circle again, right? And where's the y-coordinate? Negative root 3 over 2. So you're saying down here, because that has the ordered pair 1/2 negative root 3 over 2. Everyone agree with that? And then there's another one over here, but I'm not allowed in the second or third quadrants, right? So I heard negative, what did you say? Negative 60 degrees? That is correct, but what do you think the most common mistake is? Yeah, someone will say, okay, it's the angle that goes all the way from here to here, which would be what? 300 degrees? They'll give something like that, like 300 degrees. Now I agree, 300 degrees is coterminal. It gives you the same angle. But when you're saying that your angle has to be between negative pi over 2 and pi over 2, that's the same as saying that your angle has to be between negative 90 degrees and 90 degrees. And if you try and tell me 300 degrees is your answer, it's impossible because you're not in this. So instead of going counterclockwise around and give me a positive angle, you just go clockwise around negative 60 degrees, and then you're going to lie in this, right? So negative 60 degrees or